So today I am going to talk about parity constraint on the S matrix for hadronic system. So for this I will discuss two cases. First case is that scattering of spin 0 particles on spin half particles, right? And another case is for the decay of, this is the first case, and in the second case I will discuss the decay of spin 0 particle into the spinless particles, right? So it decays into spin 0 particles decay into 3 particles. So I will talk about it in the second case. So first of all, let me discuss the first case. So consider a two-body elastic scattering. This is the first case. So consider two-body elastic scattering. Means a particle A and B, when they gets interacted with each other, they gives rise to C and D, and say its momentum will be P1 and its momentum will be P2 and its spin will be 0 and its spin will be half integral. So let us relate with it as spin vector sigma, and here after interaction the new particles will be there, so its momentum will be P1 prime and its momentum will be P2 prime, and say spin vector associated with it, means it is according to the law of conservation of spin. So so these are the momentum and the spin vectors associated with the particles which we have considered. And if I try to look at it in the center of mass, and let me try to understand it diagrammatically, these are the two particles which gets interacted with each other and they give rise to new particles C and D. This is A particle, this is B particle, and momentum associated with it P1 and its momentum will be P2 comma sigma is the spin vector, and for C it is P1 prime and for D it is P2 prime comma sigma, right? So this is its simple diagram. And in center of mass frame, so if I talk about it in the center of mass frame, then in that frame this P1 can be written as minus P2, and let us call it as a Pi vector, and similarly P1 prime is equal to minus P2 prime and is equal to PF, right? Let us call it as the PF. And for elastic scattering, it's Pi vector magnitude and PF vector magnitude must be equal to, say, P, right? That's what we have assumed here. So now for initial state vector, so if I consider initial state vector, and it is represented by I, cat I, and it is basically Pi comma sigma and final state is represented by PF comma sigma. That's what we have considered. So under parity operation, it's not like this, but it should be written like this. Yeah. So under parity operation on initial and final state, under parity operation on initial and final state, I can write down parity operator when operates over I, it gives us eta pi, means eta p is the intrinsic parity of the initial state, and it is pi vector sigma. That's what will happen to it under the parity operation. And similarly, when parity operator operates over the final state, then eta p f minus p f sigma, that's what will happen. Now let us define the transition matrix, because transition matrix is related to scattering matrix. Transition matrix is basically equivalent to scattering matrix, as we have studied in the early lectures or in the beginning of this course. So let us define the now transition matrix. So transition matrix can be written as it was like this. It is equal to pf sigma t pi sigma. So let us introduce parity operator to it. So to incorporate parity operator to it, it can be rewritten as, means this is equal to, this can be written as, it is pf sigma, it is parity operator dagger, p operator into t, and here again. So if I do this one, then this remain this expression as invariant, because this is also identity, this is also identity. But what we will do, if we put all these together and operate parity operator with this part and this parity operator when operates over this, what will happen? When parity operator operates over it, it gives rise to eta pf, eta pi. This transform this into pf2 minus pf. So it can be written as minus pf sigma, and this pt p dagger, it will remain as it is, this part, and this will become minus pi sigma. Now since t is invariant under p, since t is invariant under t, so what does it mean? It does mean that when parity operator operates over t and here its dagger will operates over it, then it is always t. This is the meaning of invariance of t under parity vector p, right? So that means this is equal to t. So what does it mean? It means that this is equal to eta pf eta pi minus pf sigma minus pi, sorry, it's a vector should be there, yeah, it's a vector, it's also a vector, yes, it should be written like this, right? So that's what I can write it down. But for elastic scattering, parity should be equal, so eta pi must be equal to eta pf. So since we know that intrinsic parity is either +1 or -1, so that means both the parities, intrinsic parity is either +1 or -1. So what does it mean? It means that the product, this product means eta pf and eta pi, it's always 1, right? So if I put this value here, it means it is minus pf sigma t minus pi sigma, right? That's what we are getting here. So thus I can compile these two results, sorry, this result. So how do I write down? I can write down that as this pf sigma t minus pi sigma, it must be equal to pf sigma t pi sigma, right? So if we assume now, if we assume rotational invariance, then t can only depends on rotational invariant quantities, and what are our rotational invariant quantities? It is a p vector, pf vector, pi vector, comma sigma, comma sigma dot pi, comma sigma dot pf, and sigma pf cross pi. These all are rotational invariant quantities. So assuming rotational invariance, so assuming rotational invariance, we can write what we can write, that pf sigma t, it is pi sigma this can be written as this a p theta plus a1 p theta into sigma dot pi plus a2 p theta, a2 p theta sigma dot pf plus b p theta, it is sigma dot pi cross pf. So this is a This is a 2 by 2 matrix. This is a 2 by 2 matrix. In spin space, and matrix elements are, to be taken between spin wave function and it is chi f dagger comma chi I. This is for the final state and this is for the initial state, for final and initial states. Final and initial states. Thus, using rotational invariance, using variance, we have 2 raised to power 4 independent amplitude. We have 2 raised to power 4 independent amplitudes. If we assume invariance under parity, means considering parity constraint. Then A1 is equal to A20, which is equal to 0. So therefore, invariance under rotation and space inversion gives what it gives, that is pf sigma t, it is pi sigma. It must be equal to chi f dagger, it is a p theta plus b p theta sigma dot pi cross pf, that's what is there, into chi I. So hence we observe that symmetry principle restrict the form of transition matrix. So let us now talk about the second case. So second case is the decay of spin 0 particle. So for this, consider a particle A and it decays to particle A1, A2 and A3, A1, A2 and A3. This decay into 3 particles. And considering rest frame of particle means considering this in the rest frame. If we consider this in the rest frame, then 0 is its momentum. It must be equal to the sum of momentum of the other 3 particles. Now transition matrix is given as, now transition matrix is given as MP1, P2, P3, and this is equal to A1, P1, A2, P2. This corresponds to the final state A3, P3 into A0. So this is the transition matrix. Applying parity operation as we did in the earlier case. Applying parity operation to input initial and final states. That when parity operator operates over this is equal to A0 again, but when it operates over this AI, EI, this corresponds to final particles. This can be written as my equation number 1. So let us now incorporate parity to the transition matrix. Parity to transition matrix. So what do we do to do that? For that I will proceed as follows. This M, P1, P2, P3, it must be equal to A1, P1, A2, P2, A3, P3 into P dagger P, T and P dagger P. And this will not affect the equality of the matrix. And if I put these together and this operates over it and this part operates over it, and if I apply this, then, and if I use equation number 1 here, then what do? I can write down it as minus 1 raised to power 3 into A1 minus P1, A2 minus P2, A3 minus P3 into this. I can write down it as T as I discussed in the earlier lecture. So it is A. Now this will remain as it is. So therefore must be written as minus M minus P1 minus P2 minus P3, and let us call this as equation number 2. So right now consider rotation and P1 dot P2 cross P3. But since, as we know that P3 is equal to P1 plus P2 with negative sign, so this makes P1 dot P2 cross P3 is equal to 0. So hence rotational and space inversion implies, hence rotational and space inversion implies space inversion implies that M P1 dot P2 comma P2 dot P3 comma P3 dot P1, it can be written as minus M1, sorry, minus M P1 dot P2 comma P2 dot P3 comma P3 dot P1, and if I bring this towards this side, then this makes M is equal to 0. So thus we can summarize the results as so let me summarize. So thus decay of a spinless particle with even parity to pseudoscalar particles is forbidden as matrix element will be 0, forbidden if we assume invariance under space inversion. But on the other hand, decay of spinless particles with odd parity to 3 pseudoscalar particles will be allowed under space inversion invariance. Space inversion variance. Right, so that's all for this lecture.